Hello, in this video we are going to provide a discussion and overview of what is called design of experiments. Again, this is necessarily a very large and broad topic, and the goals of this section are just to familiarize you with some of the concepts, some of the background and terminology of DOE, and it is preferable that you have read through the notes before actually watching the video. Okay. So basically, and I'm not going to go into a lot of detail, what we call formally designed experiments or statistically designed experiments were invented by a man named Sir Ronald A. Fisher, which was also considered the founder of modern statistics. And Fisher was working with scientists at an agricultural experiment station in London nearly 100 years ago. And Fisher discovered, because of very poor experimental practices, despite 65 years of work, the scientists had very little to show for their efforts, and he quickly realized most of it was because the designs were poor, rendering most of their data worthless. In other words, they really couldn't establish causal relationships between the various factors they manipulated and their responses, which were things like yield. Unfortunately, there was no coherent body of work or methodology on design of experiments or how people should do them, though concepts in experimental design go, well, at least back to Galileo, but these were basically piecemeal efforts, and Fisher is the first one to put literally all the pieces together, put forth a methodology which we more or less follow today on how one should design experiments. And basically, again, I won't go into all the details. You can read the notes. Basically, Fisher said in doing experiments there are four important principles. Again, we more or less follow these today. Replication simply meant that because you're dealing with responses, things you measure that are subject to random variation or noise, it's important to replicate some or all of the trials in the experiment. In other words, if you do a single trial and you see a result that you think is really good, or perhaps you think it is really bad, it's entirely possible that all you've observed is a random occurrence. In fact, we have journals full of results that cannot be reproduced. And the reason for that, a lot of scientists today still don't replicate. So Fisher said, no, you have to replicate. And by replicating, that is, do the trial over again under the same conditions and see how much the response varies. So replication gives you a way of estimating the noise in the response. Another way of saying it is, how much does the response change on its own? Fisher also said you should do the trials in a random order. In other words, there are often hidden or unknown sources of variation in the environment, and by randomizing, that is, again, don't do the trials in a systematic fashion, randomize them. Even if these hidden sources exist, at the very least you can randomize them out and they won't be confused with the experimental effects. Blocking I will not discuss. And then finally, a key point, a very big point, is what he called factorial experimentation. This is all he meant by the term factorial. It has nothing to do with the term as it's used in arithmetic in reality. He meant you have multiple factors at multiple levels and you simultaneously manipulate all of them. Okay, and I'm going to say more about this in a moment. This was a key improvement over how most people experimented. So if I have more than one factor, I want to simultaneously manipulate them, but I have to do it in a very well-defined or prescribed manner. By the way, Fisher also developed what is known as analysis of variance, a common tool in statistics that was very useful in analyzing the results of an experiment. Okay. So basically, design of experiments, by the way, it's often called DOE. I don't necessarily like DOE because it gets confused with so many other initialisms, but in any case, we're sort of stuck with it. And basically what you do, you have some number of factors. They each has some settings. Okay? And in a very efficient manner, as I said, you manipulate all the factors. And basically what the goal is to figure out which of the factors or effects are significant in terms of how they impact the response. And another result of these experiments, we can often build predictive models that help us improve or control a response. So DOE offers a very structured and efficient approach to experimentation, and in fact, in some complicated process, it's virtually the only way you can establish things like cause and effect relationships. I should also point out that if you've heard of clinical trials in medicine, clinical trials are basically forms of designed experiments. So design of experiments is a pervasive technique in many areas of science and engineering these days, and knowledge of it is very important to doing things such as establishing cause and effect and bringing about process improvement. Okay. So just some quick terminology. The characteristics we measure, sometimes we call them critical to quality characteristics, are often called the response variables. They're also called dependent variables because in some sense their behavior is dependent upon some input factors in the system, and those are often things that we experiment with. And then the variables that we manipulate, call them the inputs. The factors are often called independent variables, and quite often, frankly, are just called factors. And it is the factors that we manipulate to see how, by manipulating the factors, we can change the response. And of course, if I want to establish how a factor changes a response, then each factor has to have more than one level. If you don't change the levels of the factor, then you have no idea how that factor might influence the response. To give you an example, and this is actually from a case study where they're trying to improve compact fluorescent lamps, so they look at 3 types of phosphor coatings on the inside of the lamp and 2 levels of pressure. It turns out lamp pressure is actually very important to lamp performance. Okay. So in terms of these input factors, they can be nominal, that is, they can be just levels like coating 1, coating 2, coating 3, and they can also be continuous, such things as, say, lamp pressure or temperature and so forth. Okay. So at this point, again, I will not talk to every slide. I would like you to read through the notes. I've already mentioned replicates. Again, this is nothing more than repeating some or possibly all of the trials in the experiment if the experiment is not too big. And the goal of replication is to measure how much noise exists in the response. Okay. Basically, if you experiment under the same conditions and you see a distribution of response values, that tells you how much this response just changes if you stand there and observe and do nothing. Also, quite often for continuous factors in experiments, we often just use a scaling of +1 for a high level and -1 for a low level. You don't have to explicitly worry about this, but often, especially in training, we like to use this plus and minus 1 notation because it helps people to better visualize the structure of the experiment. Now, I mentioned Fisher pioneered what we call factorial experimentation. In fact, he really isn't the first person to do it. There were some people in the 1800s, some scientists who used a similar idea, but he is really the first person to formalize the concept and show how to do what we call factorial experiments. Well, up until the time of Fisher, most experimentation, and some of it is still done this way, is called one factor at a time, or OFAT. That is, one may have multiple factors. One factor is changed, the others are held constant. So in some sort of sequence, one changes a single factor while holding the other factors constant. In general, this is actually a very bad idea and comes from some actually incorrect 18th century thinking about cause and effect. Again, this is not a course in the philosophy of science. But basically, I'm going to illustrate it with a simple example. And again, I will use the idea of compact fluorescent lamp design. So we have a factor A, lamp pressure at 2 levels, and another factor, powder weight. This is basically the density of the phosphor coating. So to begin, I'm going to experiment with lamp pressure, but I'm going to hold powder weight constant at its high setting. In other words, the denser coating. So notice in this design, okay, by the way, to show you, there is replication. So that's a good thing. So remember, powder weight is constant. So we do low pressure, high pressure. Notice there is variation between the replicates. We just call it noise. There's no explanation for it. And then we look at the averages. So at low pressure, the average lumens output was 1,615. At high pressure, 1,790. So this would lead one to quickly decide, well, clearly higher lamp pressure is always better. And this is indeed the nature of one factor at a time experimentation. So at this point, the researcher says, I'm done with pressure, always run it at the high setting. Okay. Well, we're going to hold pressure at its high setting, and now we're going to manipulate powder weight. So again, notice we do replication. So we do 2 replicates for low and high weight. Again, we see there is variation between the replicates. Again, this is noise. In the ideal world, each replicate lamp would have exactly the same output, but this is not an ideal world. This is the real world where things just randomly vary, often for we don't even know all of the reasons. In fact, part of experimentation is try to figure out at least part of why things are varying. So notice once again the difference between low weight and high weight. By the way, notice the difference between the low weight and the high weight average is actually much bigger than the variation in the replicates. In other words, it looks like noise by itself would not explain the difference between running at a low weight and a high weight. So from low weight to high weight, we're differing by about 200 lumens, while the difference between the lamps are somewhere between 40 and 50 lumens. So it looks like this may be a real effect. So basically, using the OFAT approach, we are now done. Okay. We run at high pressure and high weight. That will give us the best results. Well, that may be how one factor at a time experimentation works, but there's a problem. They've actually missed some runs. In particular, they never looked at low pressure and low weight. In the world of OFAT experimentation, one would never even waste one's time looking at this result because it clearly would be inferior. Well, guess what? Let's go back and do that run. and by far the best results have been achieved. What is going on? And this is the problem of OFAT experimentation. In physical systems, the inputs, or our factors, typically don't work individually. That's a great flaw in the thinking of one factor at a time experimentation. They work in combination or in concert. And we call this interaction behavior or interactivity. That is, how one factor influences the response may depend on the settings of one or more other factors in the system. Interactions or interaction behavior is the rule, not the exception in design of experiments. And one factor at a time experimentation typically is frustrated and frankly often leads to failure in the face of systems where there are strong interactions, which are most physical systems. So this chart, it's called an interaction chart. I'm not going to spend too much time on it. I just want to give you a brief idea. On one axis, you plot one of the variables, doesn't matter which. So I'm going to plot pressure. Remember, it has a low setting and a high setting. Okay. The y-axis is the measured response, and then we plot all the measured results of the experiment. Okay. And then, to help visually understand interaction behavior, we draw a line connecting the averages for each level of the second variable. So notice, if we go to high weight, just follow the line. If we're at high weight and we go from low pressure to high pressure, we improve, okay, the output. In other words, the effect of powder weight is positive. But what happens if we use a low weight? Notice it's just the opposite. The best result actually occurs at low pressure and low powder weight, and overall the effect of powder weight is negative. This is a typical interaction. So one factor at a time experimentation often leads you to incorrect conclusions. The only way to really estimate interactions is through the use of factorial experiments. Okay, so that was called an interaction plot. In a design of experiments course, we spend quite a bit of time on them because they're very useful to the analysts in diagnosing the behavior of the inputs to the system. Okay, and just basically the way they could have designed this experiment is what we call a 2 squared factorial, 2 factors at 2 levels each. And if they replicated each trial twice, that would be 8 runs, and they could easily estimate interactions. In point of fact, this is usually much more efficient than just trying things in some order, like one factor at a time experimentation. Generally, you end up doing less experiments. In fact, almost always, if you do the factorial approach. And I also mentioned there's another approach, which is the worst of all, which I call haphazard, where people just jump around, try this, then try that, then try something else. And usually what happens at the end of this, they've collected a lot of data, put it in an Excel spreadsheet, and basically stare at it, having no idea what to do with it. And basically they might bring it to a statistician like myself. We'd look at it and say, because there's no structure to this data, there's no way to establish any cause and effect. This is part of the problem when scientists or experimenters have no formal training in the subject. They often waste a lot of resources doing experiments that lead to no real useful results. Somewhat like the people that Fisher dealt with at the Rothamsted Station, where, by the way, they tended to do one factor at a time experiments, and they tended to never randomize. But that's another story. Okay. So basically, when we talk about designs, there are a number of categories. Again, this is meant to be just a brief overview. There are what we call screening designs. These are typically smaller designs that are typically used when one has a lot of potential factors. You'd like to screen some of them out, get rid of them, and say, no, we don't need to study them any further. They have no effect, and then focus on a smaller group. Okay, and these are used mostly for what we would call exploratory experimentation, just trying to understand what inputs to the system are most important. Okay, there are designs called definitive screening designs. These are actually a fairly new development. Again, in a design of experiments course, I actually spent quite a bit of time on them. I just wanted to give you a quick overview of them. Fisher's designs were what we call full factorial. You ran all possible combinations. And the problem with full factorial designs, they can actually get very large very quickly. And a common type of full factorial design is sometimes called a 2 to the k. These are very efficient, and they are the following. Okay, the 2 represents the levels of each factor. The exponent k is the number of factors. So if I had 3 factors, each at 2 levels, that would be a 2 to the third, and there would be 8 unique combinations apart from replication, and we might replicate the whole experiment, or we might replicate parts of it. Okay, so on slide 19 is an example of a 2 to the third factorial replicated twice. Okay, you'll notice an example I'll just look at. Just by chance, by the way, this design has been randomized that runs 12 and 13 turn out to be replicates. Okay. It turns out that these large designs, these 2 to the k's, are very large once k gets beyond basically 4. They become very big. A 2 to the 5th has 32 combinations, and frankly, half of them are mostly a waste of time. So sometimes what are run are called fractional factorials. Basically, you take the 2 to the k design and you cut it in half or split it some number of times to develop a smaller design. There's quite a bit of background required to fully explain fractional factorials, and to some extent they're starting to be replaced by these things I call definitive screening designs. But I'll just illustrate briefly on slide 21. This is a 2 to the 6th minus 2. Here's what the notation means. A 2 to the 6th has 64 trials. I'm telling you, a complete waste of time to do 64 trials. Well, we've taken and split the design in half 2 times, so we're actually running a quarter of it. So what you see on slide 21 is what we call a 2 to the 6th minus 2. It's 16 runs, and this actually, by the way, is a very nice design for studying 6 factors each at 2 levels. Okay. So fractional factorials are typically used when we have a lot of factors, and even a 2 to the k factorial simply becomes too big. Okay. There are also things called response surface designs. Again, I'm not going to get into them. These are often used for optimization. And again, in a design of experiments course, we spend a considerable amount of time discussing them and what we mean by optimization. Mixture designs are for formulations like recipes and so forth. And again, I'm not going to cover them. We've talked about replication. As I said, blocking is beyond the scope of our discussion for the present. So I'm going to skip through some of this. And I just briefly wanted to talk about what Fisher called analysis of variance, or ANOVA. So he came up with this methodology to experiment, and when he was done, he also had to have a way for scientists to be able to analyze their data. And what he did, he was very creative. He took some existing ideas or concepts of analysis, combined them together, and added some of his own, and developed what's called analysis of variance. And here's what it does. It takes all of the variation you observe in your response. So overall, over all the trials, you have some, say, large amount of variation, and using what's called ANOVA, we divide that variation into two parts. Variation that can be attributed to manipulating the experimental factors, so basically caused variation, and noise. Fisher called noise experimental error. That is, when we do replication, we see variation in the response. It has no explanation. So today people tend to call it noise, but again, Fisher called it experimental error, the failure to exactly reproduce a result. So ANOVA has actually become very popular in general in statistics, and it's a way of trying to separate potential causal relationships from noise in the measurements. Its basic foundation, again, this is not our objective to dwell on this, but this is the key result of ANOVA. And it's based on what we call the sum of squares. Basically, these are variances, or they're related to variances, just like we studied in descriptive statistics. So the sum of squares total is basically the total variation. And notice it equals two components. What we call model variation, this is a term we use with the JUMP software. Model variation means all of the variation due to the experimental effects. In other words, things that we have manipulated. And then the sum of squares error, which is basically variation, or without cause, basically noise. So basically what we like to do is we compare the sum of squares model to the sum of squares error. Okay, and these are typically converted to variances, basically averages. So we have a mean square model and a mean square error. And then we take the ratio of them. Okay, this was developed by Fisher. If you've had an intro to stats, it's often called an F ratio or F test. Basically, it's a signal to noise ratio. How much bigger is the variance explained by the model compared to the noise? So the numerator is a signal, the denominator is a measure of noise. The bigger this ratio, the more confident we are that our experimental factors are explaining substantial variation in the response, i.e., we've established cause and effect. Okay. Something else Fisher advocated, and again, I won't dwell on this, but you're going to see this in future examples and case studies. That is, he advocated that you needed a model to link the response to the factors. So I'm just giving you an example of a model on slide 34 where I have two factors, A and B, and the possible effects that could hit the response. The individual effects, by the way, in design of experiments, individual effects are often called main effects. Interactions are actually represented as cross products. In fact, mathematically, that's how they're calculated. And in this case, we added an additional term. We added some squared terms in case the relationship between the factors and the response is not exactly linear. So once we have these models, we can then use these models to predict the behavior of the response, and they can actually form a basis for optimization. Okay. So again, I'm not going to go really through the rest of these notes. You can read them, but this was meant to give you a brief introduction to a very important set of statistical tools referred to as design of experiments.